Thank Hyungnyal and other organizers for the invitation as well as the impeccable organization. I'd also like to, I'm very grateful to KAIST Math Department that there is this yearly conference, Geometric Topology Fair, because I know very well how hard it is to have yearly conference in Korea. We kind of, in my department, we kind of gave up on that idea, so very grateful. Another thing I want to talk about, say is that I hesitated for a long time what to speak here, because partly because what I'm going to talk is, and I changed the title the last minute, sorry, for two reasons. Because one, I thought maybe it's a little bit of off topic. It's not really geometric group theory, but I hope that it is close enough. And the second reason is that we're still polishing the paper, so maybe it's not in a very clear and well organized, but hopefully it's understandable. Okay, so today I'd like to talk about some problem that is motivated by Diophantine approximation. So let me start with a geometry of numbers. So in geometry of numbers, one main theorem, one main topic, one of the main questions is the following. So let's say that we have some S, a bounded set in the Euclidean space RD, and what we want to do is to, what many people looked at is to count the intersection of this given bounded set with some discrete set. So the oldest question is to count the lattice points, the integral vectors inside S. Or maybe some coset of that. So let me write this way. So integral vectors plus some vector, some fixed vector in RD. One can generalize these questions to, instead of ZD, which we call standard lattice, maybe we can generalize to lattice. And by lattice, so for example, the picture would be instead of integral points in R2, maybe we have some skewed points. So for fixed V1 and V2, let me draw this way. V1 and V2 will have all the Z-span of the V1 and V2. So by lattice, let's think of Z-span of the linearly independent vectors. And when we translate by W some vector in RD, we call this lattice translated plus some vector, we call this grid. So translate, for example, you have Z2, and instead of Z2, we'll have just a small translation of all the vectors in Z2. Something like this. So maybe counting, sometimes traditionally, we, for example, we take a ball in RD and then increase the radius of the ball. Or sometimes we fix S, etc., etc. And today I'd like to talk about just one type of set S. Which we call spike. So what are they? So it's determined by an open bounded set. O will be a bounded open set. And for given O, we'll define S, which is a set that depends on O, of course. And this is it will be some inverse image of O of some flow, where, so let's just think about this not as a flow yet, but AT is some element, which is a diagonal element with diagonal entries e to the C1, e to the C2, etc., to e to the CDT. Okay, so these are the diagonal entries, and all the others are 0. And let's normalize so that the sum is 0, so that the determinant is 1. So AT is in SLDR. So for one fixed AT, and maybe some various kinds of O, we're looking at this S, which looks like a spike. So for example, if you have a picture for D equals 3, for example, we can start with the upper hemisphere. Then, let's say AT, right here, AT is e to the t, e to the t, and the sum of the exponents should be 0, so e to the negative 2t. Then if you look at AT inverse of O, it's going to, this hemisphere is going to be shrink and go up, right? So we'll have something like this. Okay. So this is my, if this is my O, then this is my S. So it looks like a spike. But this O doesn't have to contain the 0. If you have O here, this is my O, some small ball above the XY plane, then you'll have a spike looking like this. Right? And it can also go down if you have a ball. So if you have points below XY plane, then you'll have both spike like this and this. So this will be a spike if our O is a ball. Okay, so we're looking at this S, and we're interested in some intersections with lattices or translates of lattices that we call grids. Okay, so how do we approach this problem? Where do we leave? The geometry behind it is the space of lattices, because AT acts linearly, right? Just by multiplication on vectors of RD. So it also acts on the space of lattices. And for convenience, let's restrict ourselves to unimodular lattices, which means that parallelograms spanned by these bases, these linear independent vectors, has volume 1. Okay? So if you look at the space of lattices, so let me write here. So X is the space of lattice, space of unimodular lattice. Then you can easily see that if you have these linearly independent vectors, if you have bases, and it's easy to see that by an element of SLDR, you can move from one to the other. So SLDR acts transitively on X. And if you look at the stabilizer of the standard lattice ZD in SLDR, it's SLDZ. So our space can identify with SLDR mod SLDC. So how does it look? It's not exactly a hyperbolic negatively curved manifold, but that's how we think about it. So it's, asymptotic geometry has very similar flavor to hyperbolic geometry. In particular, if you take D equals 2, then SL2D R mod SL2Z is the unitangent bundle of the modular surface, right? So D equals 2. X is T1 of hyperbolic plane modded by PSL to 0. Let me not write P. And so it acts AT, or more generally SLDR, acts nearly on RD, so it acts on X. So on SLDR mod SLDZ, it acts on the left, by left multiplication on the matrices. And not only that, it also acts on the space of unimodular grids. Okay, so what is the unimodular grids? Now think of SLDR mod SLDZ, but for each lattice you can translate. But how much freedom you have exactly freedom of RD mod that lattice, right? If you have two vectors, translate by two vectors, which are the same up to a vector in the lattice, then you get the same translates, right? So you can think of it as SLDR semi-direct product RD, or another way to look at it is to embed it inside SLD plus 1R and put here RD and 1 and mod the same thing over Z. Okay. And now if you look at the point here, so what I just said is that if you look at the inverse image under the projection, so all the translates of X can identify with RD mod X, right? So for example, if you have point X0, which is my standard lattice, ZD, then upstairs you'll have RD mod ZD, right? So you'll have standard torus. Whereas here, so I should have said about the asymptotic geometry of this space of lattices. So let me actually say it right now. So if you fix at positive epsilon and you look at x epsilon, which are all the lattices such that all the vectors are larger than epsilon for elements in the lattice. Sorry, I should not include the zero vector. Then this is compact by Mahler compactness criterion. And so this x epsilon is the parts that you're here you think of this way. So if you want to go to the cusp, if you want to go to the infinity, you think of a lattice which has very small vector inside. So if you have here, let's say this is another point. So this point is far away in the cusp. That means that you have a vector of norm less than epsilon. Then upstairs, you'll have a lattice. So bases, one of which is very small. So all the rest will have area very large, right? Or d-1 dimensional volume very large. So it looks like, I don't know, if you have two dimensions, then you have one vector very small and then another vector which is very large because the area is always 1. So it looks like very, I don't know how to say it, long and thin torus. So you have this torus bundle over X. Okay, so that's more or less the geometry. Right, and so now what about this AT? So we're talking about the A action on X and A action on Y. So first of all, let's start with the properties. Mainly talk about properties of AT action on X. So we think about AT as the analog of the geodesic flow on a hyperbolic surface. For example, when d equals 2, you take e to the t and e to the negative t, right? Because you have just two factors and they add up to 1. So D equals 2. AT is exactly the geodesic flow on the modular surface. And so properties. So like the geodesic flow on a hyperbolic surface, this diagonal flow is ergodic. Oh, I should have said about a measure. So actually here we have very natural measure here, which is the unique SLDR invariant Borel probability measure. So that we often call Lebesgue measure. So let's say mx. And AT is ergodic with respect to this measure mx. What does it mean? It means that if you have AT invariant sets, then the measure of that set with respect to mx is either 0 or 1. And we have an equidistribution of trajectories, so geodesics. So if you look at, you start at some point, you start at some point x here, and look at the trajectory, look at the geodesic, and look at the average, the uniform metric. Let me write this way. As t goes to infinity, it goes to the Lebesgue measure almost everywhere, every x dt. Okay, so this trajectory, so this geodesic, equidistributes. But of course, this is only for almost every. So there are exceptional ones among the ones that are not do not belong to almost every mx. So there are points there exist, but of course there are points that goes to infinity, for example. So trivially, for example, we can take d equals 2. So you have this unitangent bundle on the hyperbolic modular surface, and then you take the standard lattice, which is the unit tangent vector upward based on I. Then this x0 just goes to infinity, right? So it just escapes to infinity. Not only that, we also have the following sequence. So let's define A to be the diagonal group, which is the set of diagonal matrices of positive entries. Then there exists some xk, some sequence of points, such that the orbit under the diagonal group is compact, and yet any limit point akxk goes to the A orbit of standard lattice. In terms of the measure that we consider here, let me write mu of AXK. So that's the uniform measure on the orbit AXK. It just goes to 0. Okay. So we people call this full escape of mass. So, and this was constructed by Louis Shapira in 2015. And full escape of mass. Okay, so we have these various kinds of points. The question that I'm interested today is the following. So I started with this background that in geometry of numbers we were interested in this kind of questions. And the questions today is the following: how many lattices or how many grids we have that we can bound this intersection? Okay. So the question is the following. So we'll call those bad grids. So for given O, we look at the spike defined by O and look at all the grids. So grids are elements of Y. All the translates of lattices such that the intersection with the spike is finite. and we're interested in this set. And in particular, let's also specify the base point. So the ones that are in the fiber over X, let me call it bed O of X. Okay. So the question is whether we have many bad grids. So we call this bad grids. All bad grids. And the main question is, do we have many bad grids? This is the main question.
Why do you call it bad?
Because it doesn't happen often.
So that's the answer.
Yes, that's the answer. So no, the answer is no. There are not many. In what sense? And what condition on X do you need to give so that this bed O of X is small? Okay, so let me define a condition. So think about all these different points that can go straight to infinity, never comes back. Those that always more or less stays inside. And also the ones that doesn't go strictly to infinity, but anyway, so we have full escape of mass. So here? Finite. Yes. So naturally, we want to say that it's you look at empty, the grids that doesn't intersect the spike at all. But we have some application that we have in mind. So instead, we're looking at. Okay, we'll see. Okay, so we'll say that a lattice is heavy. X, a lattice is heavy if for every eta between 0 and 1, there exists some k compact subset in X. So let me draw it again. So you have some k such that, so you start with X and look at the geodesic. Maybe it goes far in the cusp and it comes back, etc., etc. But if you look at the time, proportion of the time that you stay inside K, so let me write it. The proportion of the time such that ATX stays inside your compact set proportion. You cannot say that it's always 1 minus eta, but at least there is an arbitrary large t. So let's say we have a sequence of ti going to infinity, such that at those points, you have some points, maybe some points. At those points, if you measure the proportion of the time that you stay inside K, is very large as you want. Okay.
So this is some sort of, this is some sort of thick-finty composition, right? So you're saying that at some point you go to the thick part is the probability or something.
Yeah, you can find K for given eta. You can find K so that at some point, maybe at time 1, you have that proportion is 0.99. And then maybe you have to wait for a long time. But at time 100, again, for 99 seconds, you're inside this K, etc. Yeah?
Proportion of time is very interesting.
Right. And that's only Lim soup. So you have a sequence of Ti going to infinity. So if you have this heavy lattice, in terms of measures, it means that let me call it path. The path of measures that are given by averaging on the orbit of X, it will go to some probability measure. So let me write Dirac delta measure on ATX. So it's a uniform measure on the orbit from 0 to t. And this goes to, in weak star, it has a weak star limit. So weak star limit. which is again a probability measure. And it is very important that we again get a probability measure. Some sort of non-escape of mass condition, some sort. And now I can state the theorem. So everything I say today is joint work with Nicolas de Saxé and Uri Shapira. And so yes, if the question is no, we don't have many bad grids if you have a X heavy lattice. So if X is heavy, heavy lattices have few bad grids. In what sense? If X is heavy, then for any O, bounded and open, the Hausdorff dimension of those bad grids that are sitting on X, so in the fiber over X, is not full. So it's less than N. Less than D. We're in RD, so we're looking at subsets of RD, and the Hausdorff dimension is not full. Okay, what is Hausdorff dimension? Let me not define it today, but one way to think about it. So actually what we are really doing is, so Hausdorff dimension, instead of Hausdorff dimension, we work with Minkowski dimension. So let me define Minkowski dimension. So this is limit. Actually, to be precise, you have to say lim inf of log of 1 over delta. The denominator is log of 1 over delta. And the numerator is log of some number of that set, delta. What is this? This is the maximum cardinality of delta separated sets in R set, bad O. So you have a set and you look at delta separated sets and you look at the maximal cardinality and some sort of exponential growth as delta goes to infinity, goes to zero is the Minkowski dimension. Okay. So Hausdorff dimension is the upper bound of topological dimension, right? Topological dimension is infimum of Hausdorff dimensions over all the metrics that gives the given topology. And sometimes it's strictly smaller than the Minkowski dimension. But anyway, so this is exactly the one that we're looking at. And we show that this Minkowski dimension is not full.
I'm sorry.
Yes.
Is there any heavy grids for
this is lattice. Pardon?
Also, general bad grids are non-zero.
This is non-zero?
Yeah. Is there any?
I guess so. Yes. Yes, certainly. We have some lower bounds actually. Yeah. So in particular, it is true for random lattices, in the sense that if you take mx, almost every lattice, so let me write it. So corollary, random lattices have few bad grids. So this statement is true for random lattices in the sense of mx. So mx, almost every lattice. We mentioned that AT is ergodic, so ergodicity of the diagonal flow gives a statement. Right. Okay, so why do we care about this question? Because we were interested in a question in Diophantine approximation. So let me say a little bit about the question that we were motivated by.
How the theorem implies a corollary?
Oh, so for mx, almost every point, you have ergodicity, the geodesic flow. So you have, yeah, it doesn't come. Yeah, it's you have something to say, but yeah. Right. So, well, we have to say something, but at least I can tell you. So, for every point here, you take a compact set that exhausts X, and for this, actually, what we show here, actually, maybe I should specify. We show is that we kind of quantified for given Ki some increasing compact set that exhausts X, and for given Ki and for given eta, some sequence that goes to 0. If you're given these Ki and eta I, then you can think of X for which, for these Ki and eta I, we have this statement. Then, for these given Ki and eta I and O, there exists, say, delta that depends on these and O, such that the Hausdorff dimension or the Minkowski dimension is bounded by d minus delta. And if you have a random lattice, what you do is you take a exhausting compact set, and for eta I, you take kind of some constant times the rest, the measure of the rest by mx, and then you can show some using equidistribution. And it's not completely trivial. Thank you. And our motivation, our application is the Diophantine approximation. Yes. Pardon?
The standard integer lattice, is that a heavy lattice?
No, it's far from heavy. So that's it goes straight to infinity, right? Yes. Yeah. Right. So yeah, right. So these are the trivial ones for which. So the ones that we started with. Oh, for those points, doesn't work. It's not true. So yeah, but for most points, it's true. So, application in Diophantine approximation. So we're interested in the vector distribution. So distribution of, say, kV and mod Zn, let's say. Okay, V is in Rn. And we want to know the distribution of kV mod Cn. So maybe I should briefly review about the Diophantine approximation of a real number. If you have a real number, you want to approximate by rationals. And using pigeonhole principle, you can show that there are infinitely many q such that this is the difference is bounded by 1 over q squared. So let's multiply by q squared. So think about it as q power 1 over 1 and alpha minus p. Okay. And it's less than 1. And this, you can think of it as alpha, the norm of alpha, modulo z. Right? So here, so modulo z, this part is modulo z, becomes modulo zn. And, oops, sorry, Q alpha, right? Yeah, Q1, Q alpha minus P. So Q alpha corresponds to KV here. Okay, so we're interested in this distribution, and actually, among the questions in Diophantine approximation, we're interested in the inhomogeneous version. So we are interested in kV minus W for W in Rn. So if you're given, say, Rn, when, for every n, when, for every n, we have, right, lim inf of, so let's think about this as 1 over 1. So we'll generalize to 1 over n. So here, k 1 over n and kv minus w. Okay, but this is modulo some integral vector. So let me write this way to note that this is distance to nearest integer. Integral vector. Okay. And we want to know if this is true for every 0. So you can think of it as a refined question of the following result is a basic result that if you take infimum or lim inf of just kv minus w, then this is always 0. Okay? So now we can think of this question as shrinking target. Why? Because what we are trying to do here is to show that for given epsilon, can you find kv such that kv inside the ball of, so let's put this, I want to show that this is less than epsilon, so let's put this on the right hand side. So radius will be k over negative 1n epsilon around w, right? And by ball we mean ball in the torus, okay? Distance to the nearest integral vector. So this is an increasing function, right, of k. So your target, the radius, the ball that you're aligning yourself is getting smaller and smaller as k goes to infinity, right? So these gets smaller. The radius gets smaller as k goes to infinity. Okay. Okay, so that was the question that we wanted to solve. And yeah. Okay, so why 1 over n? Why 1 over n here? Because that's the most natural question. Because it's already known that by Zimitzeng, and more generally for matrices by Uri Shapira again, that, so this is 15, I think, that this lim inf of k of delta of kv minus w, this is 0 if delta is less than 1 over n, and infinity if delta is bigger than 1 over n. So the real question is what happens when delta equals 1 over n. So that's why people are interested in the exponent 1 over n. Okay, so we're interested in those, the ones that lim inf is 0, or we're interested in the ones that are not 0, or it's positive. So the bad ones, let's call w. W is epsilon bad vector for v if lim inf is bigger than epsilon. Okay, so kv minus w is bigger than epsilon. Okay, and let's call bad epsilon of v all the bad grids. Bad vectors. Epsilon bad vectors. Okay, so we want to say that there are few bad vectors And what Einzidler and Zhang showed, I think it was 2011, I'm not sure, is that if you take the union of all the epsilon bad vectors, all the bad vectors, then the Hausdorff dimension is full. Okay? So that was known, and our question is, if you fix epsilon, then do you have full Hausdorff dimension? And you can see the relation here. So you want to relate these bad vectors with these all bad grids. So how do you get a result for these vectors? So let me write theorem 2 or corollary. Is that so you have to go from vectors to a lattice, right? So the lattice that we're going to think about is identity and V, the V that we were thinking here, we're looking at here, and the standard lattice, D. So here D is n plus 1. Okay, V is a vector in Rn, sorry. And so if xv is heavy, then this is true. This is false. So Hausdorff dimension for fixed epsilon v is less than. Okay. So let's see how to get there using this theorem 1. So we're going to think of translates of W by W, but for this particular diagonal matrix, e to the t, etc., e to the t, and then e to the negative nt. Okay, d is n plus 1. Right? And we're going to look at O, which is like a cylinder. So this will be Ws in Rd, or Rn plus 1, such that the norm of W is bounded above by epsilon over 2, and S is 0, 1. Okay, so if n were 2, we'll have this cylinder. One and epsilon over 2. Okay, so this is my O. So my S will be this spike, right? This is my S. Okay. So let me write it down. So S will be union of inverse image of O under AT, positive T. So for those points that are here, you go this way, right, up for large T. So let's write it as Ws, the vectors, such that, so S will be bigger than 1. So I'm looking at this spike as the union of O and the rest. So the rest will be, S will be positive, bigger than 1. And what happens to the norm of W? If you look at some norm of W here, if you look at AT, you'll multiply all the vectors W by e to the t, and S will be multiplied by e to the negative nt. So we want to take S to the 1 over n, right? So S to the 1 over n, W will be less than epsilon over 2. So this will be the spike except O. And so this is the union O. Okay, so now let's look at, for this O and for this S, let's look at the vectors. So my claim is that we can go from bad vectors to O bad grids. So the claim is that, first of all, remark that we want to go from XV, we want to go from WS to XV minus WS. Okay. And this is just Rn plus 1. And this is something like Rn plus 1, except that it's a torus, right? Quotiented. But it's a local isometry. It's better than local isometry, but it's the only thing that we need to show this Hausdorff dimension. So there's some open neighborhood that it's an isometry. So now, if you look at where we're going, from where to where, I want to say that if you have bad vector, if W is bad, epsilon bad for V, and S is, say, 0, 1, then the image, so XV minus WS, this is in O bad, is an O bad grid over XV. So let's see, why is this true? So if you look at the grid, XV minus WS, you look at the grid, XV minus WS, what is this? XV was the standard lattice, except that we had V1 in the last column, right? And Z n plus 1 minus WS, right? So let's think of a vector M and K. Then it is M plus KV minus W and K minus S, right? For K integer and M integral vector. But let's think about this as union over all K integers and M integral vector. Okay. Why are we doing this? Because S is only between 0 and 1, so this we know more or less what it is. So K minus S. What I'm saying is that we don't know, if you don't think about this, if you think about it as a one set, we don't know that it is discrete. But if you fix K, then it's discrete, right? So for fixed K's, for each K, this is discrete. What do I want to say? I want to say that if you fix K, then you know where you are. You know the height, right? And you can have only finitely many intersections, right? So if this was not true, it were not true, if you didn't have, this was not a bad grid, or not a bad grid, if this was not a bad grid, then that means that it intersects S infinitely often, right? So XV minus WS intersect S infinitely many times, right? S is, it looks like this, right? And it intersects infinitely many times. So it means that you have, and for bounded K, you have only, bounded height, you have only finitely many. So it means that you have arbitrary large K, right? This K is more or less the height, so you have K arbitrary large. And for this arbitrary large K, you have some M, some elements here, right? So some M, Z, N, such that that is inside here. In other words, this vector is inside this set, the spike. So let me write it down. K minus S, the last coordinate, power 1 over n, and m plus kv minus w. The norm of m plus kv minus w is bounded above by epsilon over 2. Right? So that's exactly what we wanted to say. Right? So this bounds. Yeah. So all right. So let me say. Yeah. Let me just write it. So this shows that if k is large enough, you can say that k of 1 over n, and you have such m, so distance to the nearest vector, integral vector from kv minus w is less than epsilon. Okay, so it's contradiction. It's not a bad vector. Okay, so that was our main motivation of the first theorem. So now maybe I should say something about the proof. The proof is quite natural. So what we do is the following. So if you have this space of lattices and the torus bundle over it, and what we do is that we start with x, and suppose that x is heavy. If x is heavy, you start with some large set Sk inside the torus over x, and you take the uniform measure on here, on Sk, this discrete set, and you look at the orbit of this uniform measure. And heaviness shows that this measure goes to some probability measure. So let me write it down. So the idea of the proof is that you can construct some mu k, which is for certain nk, some uniform metric measure orbit of some uniform measure. So this is uniform measure on Sk. So if you have this measure, kind of equidistributed orbits, kind of uniform orbits on the space of grids, then if x is heavy, then this goes to a probability measure. Now for this measure is very specific. It's constructed out of this Sk, which gives this Hausdorff dimension. And if the Hausdorff dimension of the bad grids is full, then this gives that the entropy of our diagonal flow, the relative entropy, is maximal. Okay, what is the entropy? I don't know how to say. Let me say it this way. So this will be this is the entropy of a transformation AT is same as the static entropy of mu of some sigma algebra over some another sigma algebra, and the sigma algebra you give all the information that you have downstairs. So the Borel sigma algebra downstairs, the inverse image under the projection. So here you have Borel sigma algebras downstairs lifted, and then you have some generator, another sigma algebra, which is a countable generator respect to AT. What does it mean? It means that if you look at the if you look at, you start with a partition and join the partition with AT, A1 inverse, A2 inverse, etc. Make it a finite and finite partition, that you get exactly the entropy. Yeah, okay. So anyway, so somehow the maximality of the Hausdorff dimension gives maximality of the entropy, relative entropy with respect to X. And this relative entropy being maximal gives that the set you start with, this support of mu is supported in, is invariant, translation invariant. So this Y translation invariant, because it's exactly that is the action that you have in addition to the action that you had on X. So these translations, that this part of RD inside SLD plus 1, you act here. And maximality of entropy gives some kind of an invariance. So this part was this maximality implying the invariance under the translation was motivated by a result of Eisenhüttel and Lindenstrauss, which they used for Liddell conjecture, part solution of Liddell conjecture. Yeah, anyway, so that was the crucial part. Oh, right. So the support is translation invariant. So why is it a contradiction? Because mu is supported. So mu was the Wickster limit of these elements. So it supported in the accumulation point, limit points on the forward AT orbit. That means that either the support should be a lattice, or, so maybe I should write here. The last thing I would say is that so it's a contradiction because the support mu is either Y is a lattice, or for every t, not only for positive t, but for every t, it should be AT intersection with O should be empty. But O was this cylinder, so it's not possible that this set is translation invariant, and still you don't have any intersection with this big cylinder. Okay, so you have some contradiction. So that is the end of the proof. And the last thing I want to say is that we also have example. This is an example of non-heavy lattice and non-singular, in some sense, non-heavy lattice, such that for some epsilon, the Hausdorff dimension of the bad grids, let's say X, is n, is full. So we show that actually the heaviness assumption is necessary. And another question is that we don't know if it is an if and only if condition. So that's maybe not, but we don't know. So this example is coming from continued fraction expansion. So it works only in dimension 2. And this example is given by this alpha, which is whose continued fraction expansion, so n1, n2, n3, this ni is increasing, not only increasing, but increasing in a very rapidly, so that even if you divide by I, you want it to go to infinity. If this is true, then for this alpha, the x alpha, so the corresponding lattice in Z2, in R2, is the non-heavy lattice for which you have many bad grids. Okay, so let me stop here. Thank you.